for all of you to get a glimpse of how the modeling helps in our till now where we have reached. Okay, so that's how I have put my title also, the title of the talk. That is how effective are the aerosol chemistry transport modeling studies over the Indian subcontinent, from assessing the mechanism of transport and sources to impacts on climate, health, and strategic mitigation. So. The overview of my presentation will include some modeling concepts, that is, as I told, that is particularly designed for the students' perspective. How lessons learned from recent past work on modeling studies led to improvement in current modeling of aerosols through some constant approaches developed by the group. Then after that, my third area which I will talk is impact modeling, on where we have done specific using the improved modeling to see the impacts on Hindu Kush Himalayan glaciers or PC black carbon radiative perturbations, and also the health impacts. Okay, so this is all for the general part, like, because most of you are working on the measurements, as I understand. So it is also better to learn on the modeling, so I have kept a few of the slides in this area. So as we know that atmosphere is a very complex reactive system where we have all the physical, chemical processes taking place. So if you take the measurements, as you all are, we are involved in measurements also, my group also does a lot of measurements. So it gives us information about the atmospheric conditions at a particular time and location, but they are very difficult. Like if you want to understand that about the specific atmospheric process which is affecting the concentration, like just listen the last talk on the glaciers, right? So he had difficulty in tracking the sources. So you can discuss with me, so, or you can find from this presentation. So this is where we need the application of models. Okay, because the mathematical models, they provide a necessary framework for integration and understanding of atmospheric processes and their interaction. Obviously, models, they always need, we need to have measurements. Without measurements, we cannot, we want to improve the models, we want to understand, so measurements data is required for improving the parameterization of the model, or to improve that for a particular location, how to improve their even the processes. So that is where we need the measurements role also. So particularly the chemistry transport models, why do we need them? So we need them to answer specific these questions, like what is the contribution of source A to the concentration of pollutant. So we have the source, right? Source means you have, for example, whether it is from consumption of some energy resource, like say biofuel consumption, or it is from open burning, or from industrial source, right? So it is emissions based. And then concentration, it is the atmospheric concentration. So we have the interaction, emissions and the concentration. Okay, then when you understand this part, then you also need to know what is the cost effective strategy. So you need the modeling aspect there to understand the strategy, because you can play there. So okay, if I reduce emissions disturbance and atmospheric processes are there, then how the concentration will change. So you need to develop the strategy, you need to also do the modeling. Okay, so what will be the effect on air quality of the addition or reduction of specific air pollutant emission flux? Okay, so and then suppose you want to plan, like suppose this we go with the, I also teach a subject called as EIA, like Environmental Impact Assessment. So there if you want to plan a new project or a new proposal, so you have to also take into account the area where you're launching the new project. You have to see that whether the air quality or the status of pollution there permits you to establish the new facility or not. So this cannot be done unless you have the information, or you have to set up with the modeling. Okay, so hence these questions, whatever was posed in the last slide, so these questions requires understanding of the relationship between emission fluxes and the concentration, as I told to you. So hence model involving the descriptions of emission patterns, meteorology, chemical transformations, the removal processes, they act as an essential tool for establishing such relationships. And it provides a link between the emission changes from source control measures to change in the airborne concentrations. And these kind of interactions are presented through this slide. You can see the representation of the the model, right? The atmospheric, the chemical transport model, how it looks. So you can see the particularly the how. Okay, we don't have the pointer. Yes. Okay.
That will not work.
This will also not. Okay, so you can see the mathematical model, right? So you have the yellow color shade, you can see. So you have the mathematical model and how it is linked with the emissions, sources and the predicted concentration. And this model is, you have lot of these processes, right? The physical processes, the chemical processes, then you have the dynamics, okay, the transport, how the transport is affected both by the turbulence and the winds take part also in the advection, right? The large scale transport of pollutants. So these all interactions you cannot get without the model, and here is the representation. But you can see how the complexity inside it. Each of these like say transport, it is not so easy, right? It includes such complex equations which are still not solved, and hence what we do, we have to apply specific schemes. Okay, for example, in our region, with my study, we found that the one-lead scheme of the advection that is able to represent very nicely the advection of the pollutants. So in my model, we have the one-lead scheme implemented. So these schemes are what? Because we have not reached to the solution, complete solution. So we have the certain schemes where we have the parameterization, some certain assumptions which lead us to get the solution of those equations, right? So these are very complex, and this is a research going on for many decades, I can say. Okay, and I am now here using those already developed things and using it for our region, trying to improve it for Indian region, right? And obviously, nothing could be done with the model unless we have support from the measurements. So it is required that we have the integrated measurements and the modeling work, and particularly over the Indian region where we have, we know it is a tropical region. We have strong interaction between meteorology and the pollution. If you go to other countries, okay, like I have seen, like I have been asking to the students, like winter season is everywhere in USA, in France also. But why do we see such a complex scenario here in the Indian region, right? So these are the things which makes India very it gives us a challenge. Like you solve things for the Indian region, applying your understanding, measurements, modeling, learn the modeling, use the measurements, understanding, and improve it for your strategies, right? To get various strategies. Okay, so now just to maybe I'm not sure if you may be studying somewhere. So just I will give a short glimpse. So these are the domains of atmospheric model. That means it is not like you can do the very complex modeling, right? The 3D is the most complex one. Like you can see the 3D modeling. So you have all the X, Y, Z direction. You are calculating the concentration, right? Ultimately, the concentration is the output, related concentration. But you can also start with a 1D model, simple model, right? You can always use your measurements data to develop the one-dimensional model. Say X, Z, X and the Z direction. So we have these kind of models which are there. Then in overall, the atmospheric models can be described in the two ways, like physical and the mathematical, right? So physical models are what? You can create some in the laboratory itself. Some are a replica of some atmospheric processes to understand it. Okay, so in general, it is like wind tunnel, some kind of a model can be created to understand the some processes there. So, but then it can be used for some very well-defined or some laboratory scale purpose, right? So, but for our real understanding or realistic, to make it more realistic, we have to go with the mathematical models. So, where we have again fundamental models, where we have all these physical, chemical processes applied. Then we have also the statistical models, so where we make use of the data available to you to statistically do the calculations. Okay. Then overall, when you come back about the concentration calculations, you can do it by two ways. That is the Lagrangian method and the Eulerian models, right? So in the Lagrangian model, how does it do? I think the concept is the same. What you must have studied in the physics, you have some moving framework, right? The winds, like for example, and as the winds are moving, you keep on calculating the concentration. So as the wind moves, you calculate the concentration. Whereas in the Eulerian model, you have a fixed framework and you have the concentration calculated across all the grid points. So this is the schematic of the upper one is the for the Eulerian model, where it is a fixed framework in space, whereas the bottom one is for the Lagrangian framework. So I think I will be not going into depth, but if you have any kind of specific discussion, you can come along with to me for
just one quick thing. So Shubha, just to confirm with you, when we talk about the Lagrangian, so when you see the rain outside, now these clouds are moving and then you saw that, so that's more of a Lagrangian cloud system.
How you model it. So whether you are moving with the clouds to gather.
Even for the rainfall, we see that the rainfall is falling as the cloud is moving. That we say as a Lagrangian.
Obviously, yes, that's true. Okay, so this explanation is there, but I think it will be very complex at this moment to understand if you are not working on it. So here is the glance of the equation which goes in the Eulerian framework. What you do, you have nothing but you have a simple 3D box model. Okay, so when you do the 3D calculations, this box model itself is done in all the grids, right? So if you understand this one, a simple box model, you are okay. So okay. So what we do, we have nothing but the mass balance equation. Mass balance equation goes there of the concentration of any species, say Ci, and the mass balance equation, what it will be? You have the dCi by dt, which is equal to what? You see in the box what it is coming? It will get the input, output, and the change. This is what is the mass balance equation. What is the input here? Input is your emissions, right? Emissions, so it is basically coming from the base of the box. Then you have certain reactions going in the atmosphere. That is taken care of by the Ri. Say Ri, okay, don't bother for delta x, delta y, s. That is just to dimension it correctly and all, right? So it is, if you look at, it will be dimensionally correct. So, but it is emission, the reaction. Si is a deposition, like it is also removed from the atmosphere. So Si takes care of the sink, and then you have the what is this one? UH. So what is this taking place? It is also the advection, right? So advection is taking place by the wind. So that is why U that takes care. So in this way, it is a one-dimensional. You can see that how the overall the components, the sink and the sources are taking place in creating the concentration or making changes in the concentration. Okay. So if you go with this one, if you go with the Lagrangian model, can you tell me that where changes will be there in this equation? What item or what kind of thing will be there or will not be there? Can anyone answer me? So suppose you have this is the Eulerian model, right? If you go with the Lagrangian, what will happen? Very nice. Whoever spoke, thumbs up. Okay, yes. So we will not have that U component. Okay, so I don't think I'm giving that, but it's fine that you answered. Now how it is tackled, this equation, right? So this is how, because the solution of that equation, not at all, we don't have solution to it, right? So what we do, we have the operators. Each of these processes is tackled through operators, which is, say, for example, so overall we are doing what? Del Ci by del T, which is your change in the concentration respect to time, and then it is tackled through your advection operator. You have the diffusion operator, cloud processes, all these things are tackled through the operators. What we do, we tackle each of these operators separately. Say diffusion, tackle it separately, whatever change is coming, apply to the C, the concentration, and similarly keep on doing for each of these. So this helps us in solving or creating the solution of this equation. And this is how we go ahead with it. This is called as the operator splitting method. This method of solving is operator splitting method. This is how we go. Okay? Okay, so this is how is the overall representation. So particularly my group is very much active in using, or I have been working for long with the LMDZT GCM through my collaboration, and I can say that my group has worked in improving this model for Indian region. So that is how we have, that is why I have kept here the LMDZT, the representation of the modeling, right? So it is a general circulation model, right? So, okay, so all these the different modules in the complete model are represented over here. Okay, then we also do the modeling to the regional scale, right? The regional chemical transport model. So what are these here? So here we have your, so anyone can you tell me that suppose we have the general circulation model and we also do the regional chemical transport model. So can you tell me what could be the difference between, specific difference between these two models when we do these simulations? Hmm?
Resolution will be fine.
Resolution is okay.
Boundary condition.
Yes.
Global model will not
Boundary
be-
conditions, right?
Yeah.
So Rahul is learning modeling, yeah? That's correct. So yes. So it is the boundary condition, right? We didn't see the GCM boundary. Why? Because entire Earth system is a model and it goes to the initial, we begin the model through sea surface temperature also, and then it has its own, everything, all the transport, the winds are in the model and the calculations are done. However, we take care, like the model will divert. So we have the ways to nudge the model with the observational data so that it doesn't distract away from the observation. So that is how we tackle the GCM studies for the aerosol. Okay, but in the regional model we have the boundary conditions, right? The boundary conditions are there, and so you need these boundary conditions also come from observational based, again the model, right? So we have some NSEP or many other. We also try to improve the boundary conditions going in the model, right? So this is how the modeling works. So we have the boundary conditions here, then we have your emissions, you can see anthropogenic emissions, the emission fluxes, then meteorology, and then you have the specifically the aerosols part, right? The chemical transport that takes place through, and the different processes like transport, turbulent mixing, emissions, chemistry, deposition, they all are interacting together and in the model through the equations. So overall, the purpose to show this is how this makes you an idea that meteorology is important, right? And everything is through the modeling. So meteorology is important, you have to get the boundary conditions correct, initial conditions proper, otherwise the model output is going to affect, right? Then you have also, that is why you need continuous validation with the observational data, right? As much validation you do, that much you will be able to improve the model, right? Yes, that is how it is shown over here. Okay, so then as I spoke to you that these models, they also need the schemes. Okay, so these schemes, what we use over Indian region are described. So these are all optimized schemes through, say we have evaluated many schemes. So out of these, whatever was found to be working well to describe the meteorology well, that was applied in our model. So that are all described here. So that when you do the modeling, then it is of interest. Similarly so this model is particularly the meteorological, the WRF is the meteorological model, the weather research and forecasting. So in our case, the WRF is also interacting with the chemical or chemistry transport model, that is Schimer, or sometimes we also use the WRF chem kind of thing. So this way we go ahead. Okay, then as I mentioned that these models also we also need to have the emissions, right, to correctly do the aerosols calculation particularly, and here lies the biggest challenge. Okay, so emissions. Okay, so as in the previous talks and all, we have the emissions which are affected by the activity data, the emission factors, right? So here, as of now, we see that you can see it is not so easy to calculate the emissions, right? You need to have very correct activity data. You need to have the field-based emission factors. Okay, so these makes, here again it is a challenge to get as correctly as possible the emission factors, as correctly as possible the activity data. So those are the things where we need still work going on, and we need at a very fine grade the informations. So as of now, when we look at the India-based emission inventory, why do we need this information? Because when we evaluate the model compared to observations, we have to answer that what could be the reason for discrepancy you are seeing, right? So we need to see that yes, the emissions inventory over India, they also suffer from the very high uncertainty of the order of 200%, okay, because of lack of information. That is why we have, still it is going on. It is not stopped. It is evolving, right? So we have informations improving as we are doing more and more work. So here is, I wanted to take you to the Indian Ocean experiment. Why? Because I hope, this is my understanding, that we gathered a lot of information through this experiment and my work also, and I think my colleagues and all, we came into this area and we got motivated. In fact, we got motivated through because when we were doing PhD, this experiment, the index was going on in our country. So it was held in 1999 over the Indian Ocean region, and you can see some kind of brown haze which is depicted in the figure. So people try to understand that why is this brown haze seen over the Indian Ocean region, which was supposed to be pristine region, right? Why it is seen? So to understand this, then all the world scientists, they gathered over here. I think as the other 200 scientists, our senior sir is here, sitting here. So, but I am just trying to give some insights. So, and you can see the multi-platform experiments with the aircrafts, with the ships, multiple ship cruises, multiple aircraft, satellite-based informations. They were all put up together to understand the chemical and the physical, optical characteristics of the aerosols there.
And Dr. A.P. Mitra was the
yes,
one who
A.P. Mitra sir
initiated.
was there, and I got a chance to meet A.P. Mitra sir in China. Earth Science Conference was there, where at that time I had just finished my PhD and I was invited to it.
So he is the father of this.
Yes. So that time I met A.P. Mitra sir, and he told me you be in the monsoon experiment. Some monsoon experiment I was going to start. So he told me, so in this way I had a chance to interact with A.P. Mitra sir and also with Paul Crutzen sir. We had a dinner together with Paul Crutzen also. So this way, so this was a kind of motivation to us. Okay, the challenges what we were facing here is, you can see in the other figure, the transport pathways, right? So this is from one of the very famous papers, that is Lillywald et al. 2001 or so in the Science. And actually Lillywald also evaluated my PhD thesis. It's from Germany, Max Planck, I think, Max Planck. So you can see the transport pathways, right, overall. But these transport pathways, yes, based on this, they had publication, they had a lot of discussions. They also evaluated. Now here, if again the modeling, so Lillywald applied the modeling method because they wanted to know that with this path of air, what is the chemical composition? So what is the role of Indian contribution or say South Asia contribution to the aerosols there, isn't it? But the problem with this was, these pathways are the air mass pathways, isn't it? So it may not be completely, they may give you the qualitative analysis. Yes, the transport pathways are this, but to know whether exactly this concentration is contributed by these emissions, we need some more understanding. So that is how my work got motivated, that we should do something further. And the measurements, that index measurements were used to evaluate the numerical representation of processes in a chemistry gender circulation model. And the model was subsequently applied to calculate the large-scale atmospheric chemical effects of the measured pollution. So what we needed to understand that in that oceanic region, they saw some lofted plume, right? So the question was, why this lofted plume is present there? So something they saw in the upper layers, like that, lofted. So it came to be that we should understand this, what is the mechanism of transport, and to know the geographical origin of those aerosols, and to understand the source contributions. So then we applied the modeling method. So this is the motivation to tell you that what status of modeling were done during those days. So then we had done all this, like you can see in the right corner what we have done is we tagged the emissions with the regions. So you have say IGP, Central India, Northwest India, South India, or other part of the world. So emissions itself are tagged. In the model you have only those emissions. Okay, then we had the model running, the calculations were done. So it will tell you that, okay, what is the contribution of say only IGP black carbon emissions, black carbon aerosols over the Indian Ocean. Okay, this kind of relationship. So we could understand. Moreover, it was also done, we can also do with the upper layers, right? Whether it is surface or upper layers, because it's 3D model, right? So you will see at the last I will show a movie which will show you that how the upper layer transport was taking place during the Indian Ocean experiment. Okay? So this is the role of modeling, where we can understand the mechanism of transport. So in the mechanism of transport also we saw there was a particular kind of a process taking place, like the northeast monsoon and the sea breeze. They interacted, and then it was creating a lofted pollution over the western coast of India and was transported over the oceanic region. That was also studied through the modeling method. So here here is the role of modeling. We cannot do, and also you will see a lot of transboundary transport. It was not only the Indian region was contributing to specific aerosols, for example, the black carbon. However, there were other aerosols also, like for example, organic carbon or the dust. It was not from the Indian region, but who will answer this? So here is the role. We showed explicitly that how the dust is transported from the West Asia to the Indian region, and how the organic carbon comes from in the upper layers of atmosphere to the Indian Oceanic region. Okay, so that is how the answers were given. And these are some of the results of those specific simulations. Like you can see the IGP transport, the Central India transport. So this also tells you that how the transport of particular region is going. Okay, so not describing more results here, just to show you the glimpse that how it went ahead and how we answered the questions. Okay, now the purpose of this slide is to tell that what we could get from those kind of modeling studies. What we got is, we could answer very nicely the mechanism of transport. We could say about the geographical origin of the particular aerosols. But this is the plot there is a comparison between the ship cruise measurements of Sagar Kanya and the model values. Model values of AOD is shown here. And we could see that over the region where we have low AOD values, model could perform well. However, as when the measurements were high over the near the coastal region of India, there was underestimation of 2 to 2.5 of the model versus model compared to the observations. This was for the aerosol optical depth. When we looked at the species like sulfate black carbon, we found much higher underestimation. So it was like the model could present only 5% to 50% of the observed sulfate concentrations or the observed DC. Okay, this was the scenario. We were not able to represent the measurements or observational data, right? So, this was one of the aspects to be improved, because if we don't have the correct representation of measurements in the model, then we cannot apply it for further climatic impacts or the health impact studies, right? So we needed to improve the models, but you can see the complexity. We have the emissions, we have the atmospheric process, then we have the concentration. So what to target? How to target to improve the models? That was the question. Okay, so but what we need to see from here, that what are the good points we were getting from the model, right? So the good point what we were getting was the single scattering albedo, which was found to be comparing very nicely with the observed data. Like our error was most of all within 13% or so, or even less than 5%. So one thing was we were able to tell the mechanism of transport, the geographical origin was completely consistent with the features, observed features, and the single scattering albedo, right? And what is single scattering albedo? Anyone can tell to me what is aerosol single scattering albedo?
It
Yes.
gives us the idea of amount of scattering with respect to the total extinction.
Yes, total extinction, right? Fine. So if the SSA is large, that means
There is
dominated
more
by the
scattering,
scattering aerosols. However, so in general, SSA is found to be in general 0.8, 0.9, okay, for if you have a sulfate dominating or dust dominating. However, if it is also the black carbon comes into there, then you have, it starts to increase 0.7, 0.8, right? So I think the previous graph had shown you the previous, this was from the different emission sectors. So total SSA you can see ranges between, it was found to be ranging between 0.8 to 0.9 over India. So this was for January, February, March simulations done. Okay, so these were the good points. Also, other good point of the modeling, what we found was that when we studied the transport over the remote locations, like you saw over the Indian Ocean, when it was when the ship was cruising in the far area, far remote location, we could see a good match, isn't it? Good match between model and observations. And we also saw over Himalayan region, right? The Hindu Kush Himalayan, that far remote sites. For example, we saw Hanle, Satopant and Kop, where we had measurements available of the black carbon, and there we compared the model values. It was showing a very good comparison. So this tells you what? That whereas when you compare the model over the low altitude locations, like for example Kullu, Dehradun, Nainital, we again saw the underestimation. So this tells you what? What does it indicate you? Like two things, remote locations we are able to see a good match, whereas over the regions like Nainital, Kullu, Dehradun, which are near to the source-based sources, we are seeing the lower model is underestimating. What does it indicate?
Elevation.
Right? So that means I cannot say that my processes are not, my process may have some problem, but so much deviation by a factor of 7 to 10 is primarily governed by the emissions. I need to improve the emissions to improve that factor of underestimation. Okay, this is what understanding. So this is what learning we got. Okay, so don't get, I mean to say that whatever work you are doing, everything is important. Even your model is failing, that also is important because that gives you learning. So here was a learning, what we could do, right? So this is how we gained from the model, and then we had some, also the measurements were going on at IIT Kharagpur, which we did measurements at Kolkata, Kharagpur region with all these equipments, everyone knows about them. Then other learning from the measurements. So this kind of feature you get from the measurements, right? So now this was like, for me it was like opening my eye, what happens. Like emissions are there, right? You have the model also. Now should I use the all-day mean to do some changes in the model? If I use the all-day mean, then you can see it is high concentration, very high concentration. So I need to understand in the measured data, which part of the day you have your concentration governed by emissions or by meteorological processes, right? So you have to understand that. So this kind of measurement, so you see how the measurements have helped to learn. So I could understand that during certain hours of the day, you can see some 10 to 4 p.m., 10 p.m. to 4 p.m., you have very low variation and almost flat concentration of black carbon. What does it indicate? What does it imply? Very low variation and almost flat values.
The dispersion or the effect of turbulence to disperse the pollutants in the atmosphere?
So it is the daytime hour. So it indicates that you have mixing has happened, very good mixing has happened, right? And it is now flat. Okay, very good mixing has already happened. Now, with this method, with this scenario, if I am seeing other thing and I am seeing low value, it will indicate that it is emissions based, right? Because already meteorological processes have made the change. So now if I see the change between, say, for example, model and the measurement during this time, I will say that this is because of the measurement. So this helped me to improve my emissions. That means I used only the concentration of daytime hours, not that where I have meteorological process dominating, in particular the night time and the early morning hours. So this is how the learning from measurements happened, and we could utilize only certain hours of the day to improve, to use them in emissions modification, because emissions in the model are in general from the bottom-up approach. Bottom-up, as Shubham presented, we have activity data and we have the emission factors to calculate the emissions, right? But we needed to do some different. Let me time. Okay, so I will have to stop soon. I will not be able to show the impact. Okay, so this is a method where we do the top-down, or we call them as a constant emissions. Why? Because it is done through a specific approach. Model, I integrate the model with the measurements and modify the emissions by the strategy. Okay, that is how. So this is how it is done, and hence we had the inverse modeling process developed based upon integrating model and the measurements. So this is what we call as a constant approaches. So okay, constant approach. So with the diagnostic and the prognostic. In the prognostic we go till the emissions, whereas in diagnostic we have so for example the modeled AOD is assimilated, or it is fused with the measured AOD. So if we fuse it, then we calculate back the concentrations, right, through inverse modeling. Whereas in the emissions, we do this kind of integration with the measurement, as I showed, to calculate the emissions, right? So in the emissions calculation, we have also we need to know the grids, that from where those particular concentration was coming from. So we apply the receptor modeling as well as the forward modeling and the measurements to calculate or to modify the emissions. Okay, so that is what we get with the prognostic simulations. Okay. Okay, so I don't think I will have the time to, this is all the inverse algorithm for the concentrations, and this is how it improved us. Okay, and this is how we could answer that over India, what is the concentration distribution of different species, right? So as of now we were not knowing, like when I was doing this work, I had always a question that what is this AOD composed of? Is it composed of all sulfate, majorly sulfate, dust, OM or dust? This question was prompting me to do this concept, and I could answer this, that we have, you can see the AOD dust, right? So we have certain regions of India where we have lot of dust, AOD due to dust dominating. We cannot say that AOD is completely from anthropogenic, right? We have also a lot of dust. So this is how it helped. Okay, and you can see the concentration. Concentration is majorly from dust over Indian region. Okay, if you look at the overall PM concentration. So again, if people say that PM, so it is fine, but you have to take care of the chemical components. Okay, it is dust, it is sulfate, it is black carbon, organic carbon. Just saying that only PM is affecting, so that leaves little bit of, we have to give a thought, like whether it is dust or whether it is the combustion derived particulate matter, isn't it? So anyway, I will be stopping here, and this also helped us to know the vertical distribution of the pollutants. Okay, so fine, I think I can leave now. Okay, fine then. So this was how the receptor and the source model were configured together to reach to the emissions. Okay, this is what is presented. So this is how the receptor modeling, right? The receptor modeling calculations are done to know the source grades of transport, and yes, so this is the back trajectory calculations which are used to know the grades, and then we do the back calculations of emissions to modify the emissions actually. So bottom-up emissions are the base. Without them we cannot do anything. They are the information required. But how do we further improve them? That is what we have done here. Okay, so this is how the emissions were improved. And we had these emissions obtained for black carbon, all the 12 months. And we could see that how this seasonally and spatially varying, and this were also matched with the fire counts data. Okay, we had the modified OM emissions, the SO2 emissions, and this is the back calculations of the different activity, like what it is contributing through, and then it was compared with the bottom-up emissions. Okay. And then we had the impacts, so I think these are very interesting, but I want to tell you, but anyway, now I will stop, and if you have any question you can ask me, and impacts we can discuss in person sometime. Thank you.